So, we can talk about the angle. And in fact, once we bring in the notion of angle between functions, we can also bring in the notion of angle between the corresponding sequences. So, if you have two functions x t and y t, of course, belonging to L to R, we are going to confine ourselves to that space, then the angle between x t and y t is essentially defined by the following. You see, let it be theta. We say cos theta is essentially the inner product of x t with y t divided by the norm in x 2 of in L 2 of x and the norm of y in L 2 multiplied together. Now, this is very similar to the idea of a dot product between two vectors. So, if you recall, if you have two vectors, let us say v 1 and v 2, then v 1 dot v 2 divided by the magnitude of v 1 and the magnitude of v 2 gives us the cosine of the angle between v 1 and v 2. So, in a restricted sense, you do have the notion of angle between functions, and whatever you did to construct the angle for the functions can also be done for the corresponding sequences associated with the functions, and therefore, you have the notion of angle even between the corresponding sequences. And I ask a question and I leave it to you to ponder over the answer. Are those two angles the same? Do they actually match? I think they should, shouldn't they? And I leave it to you as an exercise to actually show that they do. So, exercise. Establish a correspondence between the angle between the functions and the corresponding sequences. Anyway, our correspondence has become deeper and deeper, and whatever we have been doing with the functions, we discover can now be done with the sequences. Now, the next step is to ask, can we also think of decomposition in terms of decomposition of the sequences? So, for example, let us go back to that function in V1 that we had a few minutes ago. We had this function in V1, and we could then decompose V1 into V0, the orthogonal sum of V0 and W0. Now, just for a minute, let us keep aside the discussion of this particular function and let us look at a typical function in V1, a typical function in V0 and a typical function in W0. So, let us look at typical functions in V1, V0 and W0. Now, these are piecewise constant on the standard unit intervals. These are linear combinations of psi t minus n for integer n, and these are piecewise constant on n by 2, n plus 1 by 2 for integer n. Suppose we take a given function in V0 and a given function in W0. Now, what would the dot product be? So, what I am saying is, suppose we consider say x1 t belonging to V0 and x2 t belonging to W0. Let us focus our attention on a particular interval, let us say n to n plus 1. Let us draw the function x1 t by a solid line and this one by a dot dash line. What would a typical function look like? The x1 t function would look like this, and the x2 function might look something like this. If I multiplied these functions together and integrated, you can visualize the integral piece by piece on each of these intervals n to n plus 1. The integral on any one of these pieces is obviously 0, because the positive and the negative areas are equal, and this can be seen to be true of all the intervals, and therefore, obviously these two functions are perpendicular or orthogonal, because their dot product is 0. So, the dot product of x1 and x2 is 0, they are perpendicular or orthogonal. You know, we do not use the word perpendicular anymore. When we talk about functions, we should use the word orthogonal. What is more, take any particular function in V1 now. So, let us take the function, let us say, again focus on any one particular interval, a function V1. Let us take the interval n to n plus 1 and let the function have the value, let us say C1 for the first half interval and C2 for the second half. It is very easy to see that this can be treated as a function belonging to V0 plus a function belonging to V1, where the corresponding function belonging to V0 looks like this. So, this function is equal to this function C1 plus C2 on the interval C1 plus C2 by 2 over the interval n to n plus 1 plus the function C1 minus C2 over the first half interval and the negative of the same thing over the second half interval. So, if you take this point to be n to n plus 1 by 2, so to speak, the middle of the interval, then this height here is C1 minus C2 by 2. So, this is, you see, what I am saying is the function coming from V0 and the function coming from W0. I am just showing one segment of each of these functions. The same thing can be done for each of the intervals n to n plus 1. What I am saying is that this function whose segment over n to n plus 1 I have shown here being C1 on the first half interval and C2 on the second half interval, of course, it belongs to V1, is equal to the sum of this function C1 plus C2 by 2 on the entire interval belonging to V0 plus this function belonging to W0, which is C1 minus C2 by 2 on the first half interval and the negative of the same thing on the second half interval. So, it is very easy to see that we can in general decompose a function in V1 into a function in V0 plus a function in W0 in a unique way. And therefore, the orthogonal decomposition of V1 into V0 and W0 is easy to construct. Now, can we also make a corresponding construction on the sequences? And in fact, to some extent we have already answered the question. If you look at it, here C1 would be the value of the sequence at 2n, the sequence corresponding to the function in V1, and C2 would be the value of that sequence at 2n plus 1. Interestingly, the value of the sequence corresponding to the function in V1 at the point 2n and 2n plus 1 relate to the values of the sequences corresponding to the functions in V0 and W0, but at the points n and not 2n. So, you have the value C1 plus C2 by 2 for the sequence corresponding to this function at the point n, not 2n, and you have the value C1 minus C2 by 2 corresponding to the function in W0, but at the point n, not 2n. What I am saying is, now if you think in terms of sequences, let us do that. So, you had this function in V1. So, let us say the function is, now you know, for variety let us use Pt belonging to V1 and the corresponding sequence Pn. You have the corresponding function P0t, let us call it, and the corresponding sequence P0n, where P0 is the component in V0, so to speak, and you have Q0, let us say, as the component in W0 and the corresponding sequence Q0n. So, what I am saying is Pt is of course equal to P0t plus Q0t, but Pn is not equal to P0n plus Q0n. That is not correct. That is because the orthonormal bases are different. So, now we need to establish a relation between P0n, Q0n and Pn, and that is the next task that we would like to undertake. So, our next job is relate Pn, P0n and Q0n. And in fact, we already have an answer to that question. Let me just go back in one step here. So, we have the answer here. You see, P at the value 2n is C1, P at the value 2n plus 1 is C2, P0 at the point n is C1 plus C2 by 2, Q0 at the point n is C1 minus C2 by 2. Let me write down all these formally. So, I have a relationship there. I have almost done my job. What have we said? We have said P at 2n is C1, P at 2n plus 1 is C2. P 0 at n is C 1 plus C 2 by 2 and Q 0 at n is C 1 minus C 2 by 2. Now, let us combine these equations. So, we have P 0 n is P 2 n plus P 2 n plus 1 by 2 and Q 0 n is P 2 n minus P 2 n plus 1 by 2. And now, this brings before us a very beautiful perspective. When we talk about sequences, we can also extend that context to talk about discrete time filters acting on sequences. Can we visualize what we have done here as discrete time filters acting on the sequences? So, suppose you had the following discrete time filter. Let the input be x of n and the output be y of n, and y of n is half x n plus x of n plus 1. You know, it is a non-causal filter. Let us not worry too much about it for the moment. Let us accept it even if it is non-causal. What have we done here in this relationship? Let us reflect on the connection between, for example, this relationship here and the filter we just constructed. If you think of 2n as a variable, let us call it, let us say it is L. So, this is P of L plus P of L plus 1 by 2. Then, in fact, this is essentially the filter acting on the sequence P. So, what we are saying is, use this filter that we have here and put P n here, but then a little bit of work needs to be done at this point, because if you put in P n, let us do that, let us put in P n. So, if you put in P n there, if you put into this filter that we just wrote down here, y of n is half x n plus x of n plus 1. What we would get here is half of P n plus P n plus 1. I am sorry, n plus 1, that is correct. But we do not want P n and P n plus 1. We want to replace here. So, what should we do? We should have another system now following this, where putting x in and put out x out, where x out of n is x in of 2n. We want a system like this. Let us interpret this system. What we are saying in this system is x in at n. So, let us write down n. Minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4 and so on, and the sequence x in here. put at these points. So, as far as x out goes, so you have the index for x out. As far as x out goes, 0 comes from 0, 1 here comes from 2, 2 here comes from 4, minus 1 comes from minus 2, minus 2 comes from minus 4, and so on. So, in other words, what are you doing? You are retaining the samples at the even locations and throwing away the samples at the odd locations. Not only that, after retaining the samples at the even locations, you are putting those samples at half the location number. So, let us summarize this. Retain even samples and halve the location number. Now, this system is a new system as far as a basic course on discrete time signal processing is concerned. We need to christen it, we need to give it a name. In fact, let us go back to that system and let us give it both a symbol and a name. The symbol that we shall give it is a down arrow followed by 2, and we shall call it a decimator. You know, the word decimate actually has a very cruel meaning. I am told that in the days of wars during the Roman Empire, a very cruel thing that warriors used to do was to kill 1 out of 10 or maybe 9 out of 10, I do not remember, and that was what was called decimation. Take 10 of them and eliminate from each group of 10. That was a cruel way to deal with people, but the word decimate has also percolated down to the literature on digital signal processing. Here, decimation means retaining 1 out of so many samples. So, in this case, decimation by 2 means retaining 1 out of 2 samples. In fact, the first of each pair of 2 samples. Out of 0 and 1 you retain 0, out of 2 and 3 you retain 2. Not only that, after you retain only 1 out of 2, compress so that the sample number is halved, or if you retain 1 out of 3 samples, then compress so the sample number is multiplied by 1/3. So, if you are decimating by a factor of 3, for example, the 0 sample will go to 0, the 3 sample will come to 1, the 6 sample will go to 2, the minus 3 sample will come to minus 1, and so on. If you are decimating by a factor of 2, the 0 sample will come to 0, the 2 sample will go to 1, the 4 sample to 2, the minus 2 sample to minus 1, and so on, as we just showed. So, what do we have here? We have a filter followed by a decimator, and that together helps us construct the sequence P0n from the sequence Pn. Now, we shall see in the next lecture that we can similarly construct the sequence Q0n from the sequence Pn by using another filter and a decimator, and we shall build up further from there to do something to reconstruct Pn from P0n and Q0n, and all this shall together lead us to a totally different structure in discrete time signal processing, which we shall call a 2-band filter bank. With this little trailer for the next lecture, let us conclude the present lecture. Thank you.